Hello everyone, welcome back to another SLHL IB Chemistry 2025 video. Today we're going to be looking at structure 2.4 from models to materials. So let's get straight into the Van Arkel-Ketelaar triangle of bonding. This triangle of bonding will be given to you in the data booklet, but of course it will be useful to know how to use it. So here on this triangle we have ionic bonds, metallic bonds, covalent bonds, and polar covalent bonds, all within the same diagram. On the right over here, we can see the percentage or the ratio of each bond in terms of covalent to ionic. On the left, we have the electronegativity of the elements present in these bonds over here. And at the bottom, what we have is the average electronegativity of the bond as a whole. And this allows us to see the different properties in terms of electronegativities and bonding for these different kinds of substances. To look further into what exactly these properties are, 100% metallic bonds will be good conductors. And the reason why these will be good conductors is because they have valence electrons present. These will also be malleable and ductile because of this same reason, because as we know, when we have our elements, we have attractions in all directions towards other valence electrons from other elements within the same compound. Let's get into 100% covalent bond. So these bonds will be poor conductors due to their lack of a valence electron, and they will also have lower melting points. A bond that is over 90% ionic, because as we see, we don't have 100% ionic bonds. So a good example of these would be electrolytes. So in terms of these electrolytes, these will be able to conduct electricity when molten or in an aqueous solution, but they will be poor conductors as solids, and they will have higher melting points in comparison to covalent or 100% covalent bonds. Finally, let's look at a bond which is about 50% ionic, which would be about here at our polar covalent bonds. So a 50% covalent bond will have varying traits and properties depending on the type of bonding between the elements present in the molecule, as well as the properties of the elements themselves. Now let's take a look at polymerization. So a polymer is the long chain molecule made of several smaller chain molecules. So essentially this is just one big repeating chain. And a monomer is simply a smaller polymer. For example, these smaller several joined molecules that we see in the polymer. Now there is a method called addition polymerization in which other products are added to polymers. So an example of this would be this right here. And right now I am drawing what is called the repeat unit of this substance. And in terms of repeat units, what you will have to know is that you will have to take the simplest segment within a presented polymer. So for example, this would have just been CH2 with CH and CN repeating over and over again. You take the smallest repeat unit and you will put these in brackets. Your lines, these over here, always have to come out of the bracket, and it is always good practice to put this N number at the bottom to state that this is a polymer that will have a certain amount or N amount of repeat units. So another example of a polymer, which would be synthetic, would be polyethylene. These specific examples do not have to be memorized, but they are practical to use in terms of explaining polymers and repeat units. So polyethylene is C2H4. So this would look a little like this. Now, polyethylene is the polymer that is used to make plastic bags, and the properties of polyethylene include low reactivity with other elements or molecules. Also, do notice that this here is a hydrocarbon, and hydrocarbons are simply long polymer chains made of carbon and hydrogen, or that have these two elements present in them. So they are low in terms of reacting with other elements, making them very stable. And additionally, these can withstand quite a lot of wear and tear. They're very durable, which is why these are often used as an easy to use, very functional material, plastic. But due to this low reactivity with other elements, it takes years, decades, and if not centuries to biodegrade in the natural environment, which is obviously a common concern which comes with the use of certain polymers, such as this one. Now, that is all that you will need to know for this topic. Thank you for watching, and I hope this was helpful.